and welcome to another WJEC A level physics question. This time it's from the PH5 Unit 5 June 2011 paper, and it's question 8 from the optional module on basically AC theory. The first part of the question talks about transformers which are no longer in the spec, but for the case of people perhaps looking at this for similar work with a different exam board, I'll just very quickly run through the explanation for the first part of this question. So what we have is a transformer, and we've got to explain two ways in which the design of the core of a transformer can reduce its energy dissipation. Well, the first thing that we're going to talk about is the fact that the core is laminated. Now, lamination is like laminating a piece of paper where you sort of coat it in plastic to make it a bit more rigid. But with the core of a transformer, the iron core is sort of split up into sections, if you like, separated by sheets of plastic. So it's like a sheet of plastic, a sheet of iron, sheet of plastic, and so on. The idea behind that is that when we have alternating currents flowing through the coils for the primary and the secondary coil, we get what's sometimes called back EMFs induced inside the core, leading to what we call eddy currents flowing through the core. And those eddy currents cause a heating effect because the core has some resistance. P equals I squared R, for example. By having the core laminated, the plastic pieces don't conduct electricity, so that reduces the heating effect of these eddy currents. Something else that you can look up in plenty of places online is the idea of magnetic hysteresis. In very simple terms, as we keep on creating magnetic fields in that iron core, eventually that core can become saturated, making it sort of difficult to completely lose all its magnetism. And we have to use some energy to cause the core to lose its magnetism before the next cycle of the AC field inside there. That energy is wasted, so what we do is we just choose the material of the core to be such a material that doesn't have what we call a large hysteresis loop. And that will reduce any sort of heating losses because of that, energy losses because of that. Next, we've got a fairly standard question where we have a series LCR circuit, a circuit with an inductor, a capacitor, and a resistor connected to a 12-volt root mean square variable frequency power supply. We're going to use a phasor diagram to show that the impedance of an LCR circuit is given by Z equals the square root of omega L minus 1 over omega C squared plus R squared. I've pre-drawn a couple of phasor diagrams on the right. So on the first diagram, I've drawn phasors representing the voltage across the inductor, which is VL, the voltage across the capacitor, which is VC, and the voltage across the resistor, which is VR. You can remember the directions of those with the little sort of keyword civil. And the way that we read civil is for a capacitor, the current leads the voltage, and we always draw the current horizontally on these phasor diagrams. Remember that phasor diagrams actually rotate anti-clockwise. So the current being horizontally to the right means that VC is lagging behind it. The current is leading that voltage, so the voltage across the capacitor points downwards. Similarly, the last three letters, V leads I for an inductor. L is the symbol that we use for an inductor. And again, rotating anti-clockwise, that means that the voltage across the inductor is at 90 degrees and pointing vertically upwards with the current pointing to the right. Now, because, for example, we could write that VL was equal to I times XL, where XL is the inductive reactance, effectively the equivalent of the resistance of the inductor, and similar things for the capacitor, we could write that VC is I times XC and VR is I times R. We can also draw a phasor diagram in terms of these inductances, or resistances if we like, which is why I've added these onto the diagram. The way I've drawn this diagram, I've deliberately drawn that XL is bigger than XC, so the diagram underneath is a simplification, where XL minus XC is the resultant in the vertical direction, and we still have R in the horizontal direction. Z, the impedance of the circuit, is effectively the total resistance of the circuit, and we find it by adding XL minus XC and R vectorially, in other words by completing a diagram, a vector diagram, putting these things tail to tail and looking at the resultant being from the start to the opposite corner. Let's do a little bit of Pythagoras then, so we can see from the diagram that Z would be square root of XL minus XC squared plus R squared. But we also know, or we should know, formulas are given in our data book, that XL is omega L and XC is 1 over omega C. So hopefully now we can quite clearly see that as required, Z is omega L minus 1 over omega C all squared plus R squared. We've got to show that the resonant frequency of the LCR circuit is 20.7 kilohertz. Well, the resonant frequency is the frequency at which the current is a maximum, and therefore the impedance of this circuit, Z, is a minimum. And we can see from this equation that Z will be a minimum when the bracket is 0. Then Z would just be the square root of R squared, or Z would be R. So we can start a little proof here. The formula is not given in the data book, but it's actually quite simple to prove. We can start with omega L must equal 1 over omega C to make that bracket 0. That means that omega squared is 1 over LC, or CL, doesn't really matter, and omega is 1 over the root of LC. Also remember that omega is 2 pi f. So omega, let's undo that a second. So if we're trying to find f is omega over 2 pi. And that means our resonant frequency, as we very often write it as f naught, is going to be 1 over 2 pi root LC. I've used up a lot of space here. So it's going to be 1 over 2 pi times the square root of L. L is the inductance, 6.4 millihenry. And C is the capacitance of 9.2 nanofarads. So 9.2 times 10 to the minus 9. Placing that into a calculator, you will get pretty much the 20.7 kilohertz that we have to show in the question. This is a show question, so you basically needing to show where the answer comes from. Next, we have to explain why the RMS current at resonance is approximately 40 milliamps. So as I said a little while ago, at resonance, we have a maximum current. And that happens when Z is a minimum. And again, if we go back to the equation we derived earlier, remember that the smallest we can possibly have for Z is when omega L equals omega C, 1 over omega C, where the bracket is 0, and Z is the square root of R squared, so Z is R. So now we can calculate that RMS current. The input voltage was 12 volts RMS, and R was 280 ohms, if I remember correctly. If we do that one on a calculator, just give me a second, we end up with 0.043, so about 43 milliamps. We're going to calculate the Q factor of the circuit. There's various formulas given in the data book for the Q factor, one of which is omega naught L over R. Omega naught is 2 pi times that 20.7 kilohertz that we worked out for F. L was it 6.4? Yeah, 6.4 times 10 to the minus 3 over R, which is 280. That gives us 2.98, or we could call it 3 if we wanted to. It's not got any units. If we think about what we've got here, omega naught L is the inductive reactance measured in ohms. Resistance is also measured in ohms, so those units would cancel. Next, we've got to calculate the RMS current when the frequency is half the resonant frequency, 10.35 kilohertz. So we're going to start by calculating Z with the formula that we derived on the previous page. So Z is the square root of omega L, so 2 pi times 10.35 times 10 to the 3 for 2 pi F, times L, 6.4 millihenries, minus 1 over omega, so again 2 pi times 10.35 times 10 to the 3 times 9.2 nanofarads squared plus r squared, and r squared was 280. So 280 squared. Square root bracket covers a lot of it. So a great big long formula to type in. That gives us a value for Z of about 1280. Depends whether you use 10.35 or the exactly half of the previous answer, but it's roughly speaking about 1280 ohms. And then we can find the RMS current fairly simply by taking V over Z again. V was 12 volts, Z is the 1280 that we've just worked out. And again, putting that one into a calculator gives us an answer of about 9.4 milliamps. That's using exactly half of the resonant frequency from earlier. I believe the mark scheme comes out as 9.3 milliamps, a very slight difference, but either answer would be acceptable here. Finally, the current is exactly the same value as in part 5 when the frequency is twice the resonant frequency, and we've got to explain briefly why this is so, and this can be done without a calculator. Well, remember that XL was omega L. What we've done here is now we've doubled the resonant frequency, so XL is now double what it is at resonance. XC is 1 over omega C. So if we've doubled the frequency, we've now got half the value that it was at resonance. So if we think about what we did in the last part of the question, we used half the resonant frequency. And at half the resonant frequency, XL would have been half what it was at resonance, and XC would have been double what it was at resonance. The point is that when we calculate XL minus XC squared, that part of this expression, that's going to be unchanged from before. It's going to be the same as in part 5. Because in part 5, XL is half of what it would have been at resonance and XC was double, but here those values are basically swapped over. So it's effectively all we're saying is that XL and XC have swapped over. This means that Z is the same as in part 5, sorry. And that means that we have the same current. So once again, just trying to make that nice and clear. At resonance, XL and XC have certain values. At half the resonant frequency, XL has half of that value and XC has double that value. It's double the resonant frequency. Omega L is double the resonance, its value at resonance, and XC is half the value at resonance. The values of XL and XC have swapped over, but when we do XL minus XC and square it, we are going to get exactly the same answer. Anyway, I hope that was helpful. Let me just double check there's no last part. Yep, that's it. Hopefully that was helpful to you. If you did find it helpful, please remember to like and subscribe and maybe share it to your friends. And also, if you've got any comments, I'm always, really happy to see comments on my videos. So thank you very much for listening, and I'll see you soon. Bye now.